So in this lecture, we're going to talk about Stokes theorem, as well as a special case of Stokes theorem known as Green's theorem. So this is going to prep us for our regular in-class lecture. Stokes theorem is one of the most important theorems in multivariable calculus. So let's go ahead and get started with this. So let's first recall from Calculus 1 or Calculus 2 that we learned the fundamental theorem of calculus, which says the integral from a to b of the derivative of capital F is equal to f of b minus f of a. So one way we can view this is we can view it as if we integrate the derivative of a function over some interval a to b, that integral is completely determined by the value of the function at the edge points of the interval, namely the points x equals a and x equals b. So the integral of a derivative over an interval completely determined by the value of the function on the endpoints of the interval. Now we also had the fundamental theorem of line integrals. So in this case, if we integrated the gradient of a function, so we can think of the gradient as another type of derivative, and we integrate this over a curve given by some parameterization r of t for between t between a and b, if we integrate that gradient function, we need to determine that is the value of the function at the endpoints of the curve. So again, this is telling us the same type of thing. If we view the gradient as a type of derivative, if we integrate a derivative, the only thing that matters is the values of the functions at the edge points of the curve, so the boundary of the curve. So now we can also view this interval a to b as a curve r of t. And so both of the previous examples are basically saying the same thing, that if we integrate our derivative over a curve, all that matters are the two endpoints of the curve. And so this is basically we're integrating derivatives over one-dimensional objects, curves. So all Stokes' theorem is we take this concept to one higher dimension. So namely, we integrate a derivative. We have to decide what that derivative is going to be in this case. And instead of a curve, we're going to use a surface. So we move from one dimension to two dimensions. And now the boundary of a surface is a curve, which is something of one dimension. Whereas before we had the boundary of a curve is zero dimensional, just a point. So it's the same idea, we've just moved everything up one dimension. So we need to talk a little bit about these objects we're going to work with. So the first thing we want to know, what is a bounded surface? Well, this is basically just a surface that has a closed curve as its boundary. So for example, we see the surface S here. We have this, the surface is in green. The curve C, which is in red, is the boundary of the surface. So it has an actual like edge all the way around it. That's what we mean by a bounded surface. Recall that we said a surface is oriented as if we can choose a normal vector at each point so that it varies continuously. So basically, if you think of putting your pencil as the normal vector on a surface, as you move around the surface, you're just going to move that pencil around the surface. It doesn't flip over to the other side of the surface at any point. And so for a surface with a boundary curve, the orientation of that surface is going to determine an orientation of the curve. We're going to want these orientations to agree. And similarly, if we have an orientation on the boundary curve, there'll be a matching orientation on the surface. So depending on what our situation is, we might start with an orientation of the surface, or we might start with an orientation of the boundary curve. So the way we determine this is kind of what we keep doing all through this course, is we're going to use the right-hand rule. So let's see how we do this. So if we have an orientation of the surface, so suppose we start with our S here and we start with the normal vector n hat. Think of putting your right thumb pointing in the direction of n hat, and now curl your fingers to close your hand. And you can see whatever direction that your fingers curl in, that's the direction of C. So if my right thumb is pointing up like this, my fingers are going to curl around the curve going in this direction. So you can see the arrows going in this direction, and that gives our orientation of C. On the other hand, if we have an orientation already of C, so think of this as our orientation. Of course, we could go in the other direction, but this is the picture I've drawn. So think of putting your right hand pointing along that arrow and curling your right hand as you go around that curve. And then notice your thumb will be pointing in the direction of N. So when we say the orientations agree, that's what we mean, is that right-hand rule gives you the same matching orientation depending on whether you start with S or start with C. So now the derivative we're going to need is what's called the curl of a vector field. So if I have my vector field f here with its component functions p, q, and r, it's defined as follows. So we basically take the gradient and take the cross product with our vector field f. So our cross product is always with just vectors before, but we think of the gradient here. Think of your components as the partial with x, partial with y, and partial with z. It's not strictly a vector. This is actually an operator, but for our purposes, we just treat it the same as a vector and calculate it the same way. So if we do our normal calculation for the cross product, we cover up the first row and first column, and now we'll take the dy and apply it to r, get the partial of r with respect to y, and then we do subtracting the partial of z with q, so q sub z, and then the rest of them follow in the same way, just like you're taking cross product of vectors, except for when you have a partial, you're applying it to the function instead of multiplying it by the function. So you should remember this form here. I wouldn't memorize this form here. It's too easy to forget and mess up. So just remember the first part. So what the curl of a vector field is going to measure is it's going to basically measure the rotation of our vector field. So is the vector field rotating, in which direction, and how much? So let's see a couple of simple examples to illustrate this concept. So let's consider this vector field xi, yj, zk. So this is one we saw back in the vector field section. So if we recall, this vector field is basically just pointing away from the origin in every single direction. So if we think about this vector field is kind of exploding out from the origin. There's not any rotation at all in this vector field. So since it doesn't rotate, we should expect the curl of this vector field to be 0. So let's go ahead and check that. So if we do this calculation, notice that each of the partial derivatives, we're taking the derivative of a different variable, so we get 0 for each of those. So for instance, the partial of z with respect to y is 0, partial of y with respect to z is 0, and so on. So we do this calculation and we see we do actually get that the curl of this vector field is 0, just like we expected. So let's try another vector field we looked at before. So this one we have minus yi plus xj plus zk. So if you remember, that was this vector field. It kind of swirls around the origin, but then it also kind of expands up as it's going. So this definitely looks like it's rotating. So we'd expect to have a non-zero curl for this. And if we think of right-hand rule, how we always do, if we kind of spin our hand in the direction of rotation, our thumb's pointing up. So that's what we would expect for our curl. So notice here, if we do this calculation, we get the value 2k. And that's exactly what we saw. If our thumb would point in the k direction, if we took our fingers and moved them in the direction of the rotation of the vector field. So that's the derivative that we're going to use for Stokes theorem. So now we can go ahead and just state Stokes theorem. So let's let S be a bounded surface with boundary curve C and assume those orientations agree, just like we said before. It means our right-hand rule works out. And we take our vector field, and we're going to assume that P, Q, and R have continuous partial derivatives in some region containing S. So basically, we have nice functions here. So then we have the line integral of f around dr is the integral over the surface of the curl dotted with the normal vector to the surface. So we want to think of this side here. This is integrating the derivative over the surface. And what determines that? The value of the integral of the function around the boundary curve. So we don't get quite as easy of a thing to evaluate, whereas before we just got the value of a function at 2 points because those were the boundaries of our curve. But it is the same idea where if we integrate a derivative over a surface, we drop 1 degree to the boundary and we're just looking at the values of the function on the boundary of the surface. So it's the same type of thing, it's just a little more complicated because we've moved up 1 dimension. And just note this, we put this little circle on the line integral here to indicate that it's a closed curve. You don't necessarily have to do that. People just do that sometimes to make it a little bit easier to remember you're working with a closed curve. So let's just go through the pictures again to kind of emphasize what's happening here. So here's our surface S. And supposing we wanted to calculate the flux of some of the derivative of f through S. then what we can look at is we have this boundary curve C here. And then if we choose this as our orientation for our surface, then remember that determines the orientation of C. And so now it's just saying if I integrate the curl of f over this surface, all that it matters is what is the integral of the vector field f around this red curve C. So if we happen to take our surface to be in the xy plane, we do have a special case of Stokes' theorem called Green's theorem. And Green's theorem is very important in its own right. So let's go ahead and state this, and then we'll do an example of Green's theorem. And then in class, we'll do a bunch of examples of Stokes' theorem. So in this case, our surface, since it's just in the xy plane, we'll just let it be a region R, like when we were doing double integrals. And let's say it's bounded by a curve C. And in this case, let's force our C to have counterclockwise orientation. If we want to change the orientation, it'll just insert a negative sign. So we can deal with that if it comes up. Let's let the vector field f just be in the xy plane. So I just have p and q here for my coefficients. And again, we want them to have continuous partial derivatives in some region containing R. And if we have this, then in this case, since we gave our curve counterclockwise orientation in the xy plane, if we curl our fingers, that tells us our normal vector would be k. And since it's in the xy plane, it's k everywhere, it doesn't vary. So this is exactly the formula we had before, just simplified a little bit because we're in the xy plane. So the integral here on the right will be a little bit easier. So as I said, the normal vector here is k, and it doesn't vary with x and y. So this is just a special case. You don't really need to memorize this separately from Stokes' theorem because it just follows from Stokes' theorem by taking the specialized vector field and the fact that the region is in the xy plane. So let's see an example. So let's suppose my vector field here is 3y I minus 3xj, and C is the curve given by the following curve, oriented counterclockwise. So we can see we have a circle of radius 2, but we're only taking half of that circle. So we're going to go in this direction down because we're counterclockwise, and then we've got this line connecting across here. So that's my curve C. And so suppose I want to calculate the line integral of f around C. So my goal here is to calculate that line integral. Now, of course, I can parameterize each of these two things separately and do those line integrals and add them up, and that's what we did back in the section on line integrals. But in this case, we're going to use Green's theorem to do this in a much simpler way without having to parameterize stuff. So first we'll calculate the curl of our vector field, which in this case comes out to be just minus 6k. So you can check that calculation. So if we dot that with our unit normal vector k, I just get the value minus 6. So now if we let R be that region inside C, Green's theorem tells us that the line integral of f dot dr around C is the same as the integral over the region R of the curl of f dotted with k dA. We just saw that that curl dotted with k is minus 6. So we can bring minus 6 outside that integral. And then we're just integrating dA over the region R. And the integral of dA over the region R is just the area of R. And we saw R is a half circle of radius 2. So that means the area of that circle is 2 pi. So our integral here is just minus 12 pi. So you can see this is much easier than parameterizing both of those curves and doing those line integrals. This is basically just a very simple calculation now to get this line integral. So we'll see so this is an example of how to use Green's theorem to calculate a line integral. We will see a practical application in class of how we can use the line integrals to actually calculate areas. So that's also a very interesting application that we will see.